too close to this. Hello, hello. Is this okay? Taste, taste.
我们是北艺的交换学生，然后我们只能用纸本的加签方式。
那可能签不上。
这没有办法签嘛？就是一定没有办法。还是我们因为
几率很低，因为其实基本上快没有空位。
哦，好的好的，好，谢谢。
it's time. I guess it's time to start. Can we close the door? 帮老板关上。Yeah. So people are still coming in. Yeah. Good. Okay. Yeah, everyone please have a seat. This is a very crowded room. And I guess let's get started. So let's go back to the first slide. Wait, let me make sure. Yeah. Yeah, so welcome to the Signal and the System class. And I'm the instructor Han-Hsuan here. And yeah, so let's start with the organization. So we have the organization slide. So this is our textbook. Basically, the important thing is this. We are doing this open hand textbook. Although we don't, we follow general structure of the book. Although we will be using the lecture slides and the homework will be textbook portions, but we will type it out. Okay. And here are reference books. A reference book you can also look into to learn more about signal and systems. Yeah, for the textbook there are many editions, but I don't think it matters too much because we don't actually look into material of the book too much. But yeah, it's still nice for me to do the advertisement of the book here because we are using a lot of material related to the book. So yeah, please support whoever write the book. Okay. Yeah, that's about textbook. And here is the schedule of the class. It's a bit different from this year. Anyway, so we will have midterm and final. Okay. And yeah, so these are the chapters we're going to cover: 1, 2, 3, 4, 5, 9, 10. And the important thing right now is the midterm is going to be set at week 9. And the final is a bit tricky, so we are on 16-week schedule. But I think we might have trouble finishing everything. So for now, I will say final is a 17th week. Okay, so we'll finish Team Tree in 16th week, and the final will be on 17th week. Okay, and this is a bit funny. So I think we'll cut chapter 4 in the middle. So we'll teach you about chapter 4. So this is the Fourier transform. Yeah, we'll teach chapter 4, and so at whatever point we stop on week 8, then we'll stop and we'll have the midterm on week 9. Okay. And for the course information, so first is evaluation. This course I don't take attendance, so you don't really need to come into classroom. So the evaluation are basically mostly on the test. So midterm will be 14%, final 45%, and whole year 15%. Yeah, so you see there are a lot of evaluation on test. And we have a course website. It's on eLearn. And here is the link to eLearn. We have a lot of material on eLearn, so the slides will be posted on eLearn, and homework will post on eLearn. And I think you can also submit homework on eLearn. And also we'll have link to course videos on eLearn. Okay? But also, the course video are just streamed on YouTube, so you can also just look into. This is my official the school YouTube channel here, and so if you go to the YouTube channel, you can see the latest course videos. Okay? And if you cannot come in person, this is something I set up during the pandemic. So if you cannot come in person, the lecture are actually also streamed on the YouTube channel. It's streaming right now. Yeah. Okay. And the course content will be mostly, it's going to tell you about signal and systems. But so we are mostly talking about mathematical concepts, so mathematical concepts and proofs. But this is actually an engineering class, so we will try to give some real-world motivation for all the concepts and for all the mathematical concepts. And so this is CS department course. So we do have just a little bit of programming here. Yeah, I think if you take this in EE department, then they have rigorous teaching on how you write everything in MATLAB. But here we'll just give you a small introduction on MATLAB. So I think on week 7, okay, yeah. So around this week 7, then we will have a MATLAB assignment because it is spring break, so you can learn MATLAB on spring break. Yeah. Okay. So let's write it here. So around here you will have one MATLAB assignment. It's going to be really easy, but this give you some programming familiarity with the course material we taught here. Okay. And homework policy, we have a lot of homework. So we have weekly homework. The homework will be posted and collected on every Friday, and even including this week. So this week we will have one homework out, and you will need to turn in the next week. And I think around the exam is a little bit different. So around midterm and the final, then yeah, on the midterm week you don't need to turn in homework. So yeah, so around here maybe we'll miss one or two homework. Okay, and other than that we have homework every week. And yeah, so you can turn in homework in class, or I think you can just submit it into eLearn, or sometimes you can email to the TAs, but that might be a bit annoying for them. Yeah. Yeah. Let's finish the homework policy. So in general, we don't take late homework, okay? Unless you argue very hard with TA. Yeah, and to compensate for like you have some emergency, then we say like one of the homework doesn't count out as final grade. Yeah. So yeah, unless you have really good reasons, we don't take late homework. Okay, this is a general policy. Okay, and for the context, so the professor is me. This is Han-Hsuan, and this is my office, and so I'm at the Delta building next building, and this is my email, and we have our two TA here. So first is Zheng Guanfu. And here his building is just up floor there, and this is his email. And we also have Lin Yuce here. And yeah, his office is also upper floor here, and this is his email. Okay. So yeah, if you have homework questions, you should go to TA first because they are going to be a grader. Okay. And yeah, you can also ask course questions to them. They should be really good. Okay. And yeah, then this is a page that everyone cares about HR enrollment. Okay, but it's actually kind of late right now because I hit a bug. Okay, so the policy here is you should apply on the 电子表单系统, unless you are, I guess unless you have like some special need. Yeah, in general you just apply on 电子表单系统, and I will make a judgment on that. But I don't know, fortunately or unfortunately, I hit a bug yesterday. So actually, I already signed a lot of people yesterday, and we are almost full right now. So yeah, so this slide is kind of doesn't make much sense. But anyway, the policy is that I will try to accommodate for CS department people, but we have a very few slots left here. So you probably can see why we have a limit. That's because our classroom has a limit, and we are pretty crowded here. So yeah, so we are limited by classroom. I think it's 100 people, and yeah, we're almost full. So sorry about that. But anyway, I think this is also related to Jiaqian. So some of you might hear that this year this course was giving really good grade. Okay, so that was kind of a mistake, and I will say here right now the grading will be tougher this year. Okay, so yeah, it will be not so easy as this year. Okay, hopefully this discourages some of you. Yeah. And anyway, so the rule of HR enrollment, although it doesn't matter much now, is I will try to accommodate for CS department people because, well, this is a CS department course. And yeah, I will try to decide around end of this week, although it's almost already decided. Okay. Okay, so I think that's about the organization of the course. Any question? Okay. No? If there's no question, we'll go to actual course material. Okay. Yeah. So this course is about signal and the system. So what are signal and what are system? Signal is any variable that carries information, and variable is any variable carrying information, but in particular, it's a variable that's function of some time or space. Okay, so schematically like this. So you have some x, maybe this is position, maybe the position of something that depends on time, and this is a signal. So it's some variable. For example, the position here right now, and it's some variable that's a function of time or space. So it's a function of time here right now. Okay. So that are signals. You can think about there are a lot of we're going to give a lot of examples about signals. They they represent a lot of things that in nature and in engineering. And then we have systems. So what are systems? Systems are something that process signals. So mostly this is abstraction of some engineering process we built that takes some input signal and give some output signal. So we want to process some input signal and give a corresponding output signal that we want to learn. So for example, we have a signal that we have this, and then we have this system. Some maybe electronic component, and we have output signal. So for example, like this. Okay, and more mathematically, so what are signals? So signals are just functions. So the functions of some variable. So for example, it's on x of t. Okay, and then system mathematically is something really funny. It's a function on functions. Okay, so remember we say so signal are functions. Functions we probably all know. Function has input and output. So here with the input x t, input t, and output x of t. And system something funny is a function on function. So you will change one function to another function. Okay, and now this is something funny about the notation we are going to use in this book. Okay, so we say system change some input signal. So we have so input and output are both signals. So we input signal x of t, output signal y of t. So for example, we have x of t here, and you go through the system and go to y of t. Okay. So x of t, y of t, those two functions are the input and output to the system. And what's funny here is what's the system here. System here is actually just this one arrow here. Okay, this is kind of bad notation because we don't really have a name or even a good symbol for a system. So to express systems throughout the book and the lectures, we are just going to use one arrow. Okay. So yeah, this is kind of bad notation, but you will need to get used to it. Okay? So system is just this one arrow here. Okay? And yeah, it's a bit confusing, but yeah. So you need to remember when we talk about system, is funny. It's just this small arrow here that takes some input to some output. Okay? And yeah, so we are a lot of time we are just going to specify system by this. So the system will be this arrow, but we'll describe this arrow by what's the output in terms of the input. So for example, this is how we describe a system that take a derivative. Okay? So we say if your input is x of t, this system take input x of t and give you output y of t. And the system, what they do is the y of t is going equal to dx dt. So this is a system that takes the input signal and output the derivative of it. Okay, yeah. So this is our system. It's a small arrow here, but we will describe the relationship between output and input to describe this system. Okay. Any question? Okay. Yeah. And yes, the examiner not so important right now. Okay. And oh, I guess we can say yeah. And so here, the one concept is I said it's a function of something. Okay. And for now, yeah. And in this example, this is a function of just one independent variable. So it's a function of time. And we can also have like different characteristic on this independent variable. So it can be discrete and it can be high dimensional, etc. So for example, we can also have different signals that we have like continuous time signal or discrete time signal. Okay. Okay. So the example here was like a continuous time signal. So our signal, this variable depends on some continuous independent variable. So this t is continuous, is all real line. It can be minus infinity to plus infinity, it can be 0.5, it can be square root, etc. But a big class of signal we study is also this discrete time signal. So you can see we take this time only at a discrete point. So this is 0, 1, 2, 3, 4, 5, 7, and -1, -2, -3, -4, -5, -7. So the signal only have information on those discrete points. So we have x of 0, x of 1, x of 2, etc. And this is useful because in our digital systems, so for example computers and your phones, etc., the signal are mostly stored as discrete signals, right? Because you need to take the clock cycle, etc. Okay? And then here are some notation to distinguish between continuous time signal and the discrete time signal. We use the parentheses and the bracket on the independent variable to distinguish between continuous time or discrete time signal. So for example, we have those x of t, y of t, z of t, a of xy, and so those are all continuous time. So those t and xy are continuous, and then we have a discrete time signal. Then it will be x of n, y of n, z of n, a of n, etc. Okay, I guess we also change from t, x, y to m and n usually. Okay, although yeah, so continuous time then is parentheses and the discrete time is bracket. And then let's have some real world motivation about signals. So we say that a lot of real world phenomena are described by signals. So for example, this is something that E department likes a lot. So the circuit, a lot of variables in circuit are signals. Okay? So this is probably the most canonical example of signals. So signals in electronic circuit. So let's see, we have the voltage, resistance, and capacitor here. So the voltage and the current and the charge on the capacitor, those are all signal of time on this circuit. So you can think about we hook up this circuit and how much electronic flow, how much current will flow with respect to time, and how much charge will charge up here, etc. Okay, so that are signals, and other than EN example, we can also have other physical examples. So your car moving is also a signal. So the location, velocity, and the acceleration of your car is also a signal. Okay, and then here we can also jump ahead a little bit, and we can think about associated system example here. So you can have a system that calculates the velocity of the car from the location. So the velocity signal of the car from the location signal of the car, right? That's just the derivative system we have. So if you take a derivative of the location of the car, then it will become the velocity of the car. Okay, so you see why you want to process some signal of your system. Oh, sorry, process some signal of with your system. Okay, and more physical examples, or maybe a speech. The speech of someone, or even the speech right now I have right now is also a signal. It's a continuous signal. So we can record the air pressure as we speak, and if you draw it out like this, then this is also a signal. It's a continuous time. And there are many other more signals. So maybe the temperature right now, the air pressure, the light, etc. Okay. And then we also have an example of discrete signal. This is also a signal in electronic systems, or maybe a picture in our computer. So a black-white so a black-white picture is easier. Okay, so black-white picture is also a signal, and so it's a signal on actually two-dimensional discrete space. Okay, so we can think about the signal value as some number between 0 and 255, and so we have this bit map here, and every block we have the signal value between 0 and 255, and so if it's white, then it's 255, and if it's black, is 0. Okay. And so a picture can be just think of as a signal that is discrete signal on a two-dimensional grid. And we have a more discrete signal example. So for example, we have the stock market index. Okay, stock market index, and actually kind of depend on how long you take average. But say you can have like a weekly stock market index, then every week you will have one one data point here, and then you see that is a signal with respect to time. And then maybe you have a shorter time average, then you have the stock market. I think this is 1 day, yeah. Then you have the stock market signal. Okay. And yeah, so we have more examples, or maybe color image and a digital video. And an interesting phenomenon is you see that a lot of those discrete signal are actually kind of continuous signal, and but you take a sample or average. Okay? So you can think about if whenever you have a continuous time signal, so like this, then you can take samples of it. So you just take those discrete sample points, and you will get a discrete time signal. So for example, our speech signal here, then you can take a very fine sample, then then you will become a discrete signal. Okay. And this is how you record signals in our computer system, because as we say in our computer system, we store data as discrete as discrete points. But when we try to approximate the real life or nature signal that are continuous, then we take samples. And how to take samples is an interesting topic by itself, but unfortunately we don't have enough time in this course, so it's actually in a book, but we will not cover the chapter that talking about how you take samples. But it's just something interesting you can know. So more example about sampling. So for example, population, we can have the monthly population of a country, and that will become a sample of this continuous time population signal. And maybe a temperature averaging every hour, every day, and that will also become discrete signal for this continuous temperature signal of maybe this room. Okay, and finally, dimensionality of the signal. As you will see, so this dimensionality is the dimensionality of the independent variable. So remember, the variable we're talking about is like x of t. Okay. Sorry. Pen. Yeah. And so dimensionality. So maybe this is x of t, and so maybe this is a of xy, and maybe this is a of xyz. So dimension is how many independent variable you have here. Okay. So so if one independent variable is one dimension, and two is two dimensions, three is three dimension. Very intuitive, and we have different example. But this is not too important here, because most of the course will focus on one-dimensional signal. Okay. So dimension mostly will be one, and that one independent variable will call time. Okay. Question. Those are signals and some of the examples. And then finally, system. We can also think about systems in real life. So as we say, system is something that change. Mathematical system is something that change a signal to a signal. But in real life, if we think about engineering, system is usually a physical device. So it's a collection of components or subsystems, and you want to connect those systems together to to handle the signal in the way you like it. So here is a very good example. So it's a 19th century telephone. Okay, so the first wireless telephone here is a very good example of a system. It's a telephone, so it will take some. It will take us the sound signal from the air. So take the air vibration and change it to corresponding electronic signal. Okay, so take so it take in the air pressure signal and change to corresponding electronic magnetic wave signal. So you can send all the wireless signal to the telephone receiver, and you have another system hook up. Then last season will do the reverse. It will change the electronic wave signal back to the sound signal. Okay, so you can see the systems a lot of systems are just the electronic device we built to handle signal as we want. Okay, and so those are all-time systems, and non-systems are even more complicated. So, for example, your credit card system and credit card and the card reader is today is a very complicated system. So, this credit card reader will read read your credit card information and also read how much money you owe and send out another output signal to the bank and take money away from your account. Okay, and even more complicated system is operating system. So our favorite or not so favorite Windows system. Okay, so those operating system you can also think about. So just this operating system on this PC. So this laptop is a system that takes the input of my keyboard and the mouse input. So I give it the keyboard and the mouse signal, and you will output the signal just up on the screen. And yeah, we give corresponding output signal, so you can see my pointer moving here. This is the output signal I want to give. Okay, so we have a very complicated system now. Okay. Okay. So that's about the real-world motivation for signal in the system. And now we turn a lot to something very high level. So so those are nice real-world motivation, but a lot of the course is actually mathematics. So what do we do in those mathematics? On very abstract level is we want to analyze the signal in the systems. And to analyze the system, something we want to do is the transformation of information. So this information, the information are like, so we think about signal as a collection of information. And the transformation we do is kind of a generalization of this linear transformation. So for example, if we have two data points, x and y, then we can always do this linear transformation. We can say, well, we have x and y, then we can write out two variables a and b. So we have variable x and y, we can write out variable a and b. So a equal to x plus y, b equal to x minus y. And then we see that a and b and x, y really have the same information. You kind of just look at them into different perspectives. So because if you know x and y, you can always calculate a and b very easily. And if you know a and b, you can also calculate x and y easily. You want to reverse those equations, this is just on high school math or middle school math. Right? So if you know a and b, and you know they come from x, y with these two equations, then you can solve those two equations and they see x is just a plus b divided by 2 and y is a minus b divided by 2. So for example, you know x and y are number 2 and 1, then a and b are just 3 and 1. And if you know a and b is 3, 1, you can know x and y is 2 and 1. Yeah. So a lot of courses we try to do this sort of thing. We try to have information, a whole bunch of information, maybe some signal, and transform it to another set of another signal that really have the same amount of information as the original signal. And why we want to do that is because on the new transform signal, then we can analyze the system better. Okay. But this is really jumping ahead a lot. This is about chapter 4 and 5. We'll see it. Is it? I think, yeah. 3 and 4, we're starting to see this transformation. Okay. So the jumping ahead of the course. Any question? If not, then I will try to do something very dangerous here, which is change the slide. Let's see. Okay, yeah. So I'll try to change the slide here. Let's see. Chapter 1. Okay. So we go to actual slide. That's chapter 1. And let's see. Is it still working? Seems so. String is still working. Okay. Then chapter 1. Yeah, we are going to talk about system and the signals in more mathematical detail. Okay. We don't have much time left, so let's just talk a little bit about this. Okay. And as we say, we will yeah. So I guess let's just start. Okay. Yeah. This slide we kind of already see. So we are going to talk about signal and system. And once again, signal is a function basically. Signal is any variable, and that means it that carries information. That means it's a function of some independent variable. Okay. So here with a function x, that's a function of this independent variable t. And system, once again, this is a funny arrow here. System is something that processes an input signal to an output signal. Okay, I should highlight this. Okay, so system is something that takes input signal to and generate output signal. So system here is just this arrow, and we describe this arrow by saying how the output is related to the input. So for example, output system y of t is dx dt. So the system is doing derivative on this input. Okay. And so I think for this chapter not really. I guess so for now we focus on the signal that we care most about is a signal that with only one independent variable. Okay. So most of the class and most of this course will actually focus on signals that only has one independent variable. Okay. And the independent variable in real life might be a lot of different things, but they will just call it time in general. Okay. So one independent variable and that's time. Okay. Okay. And so it has the signal has one independent variable, but that one independent variable can still be continuous or discrete. Okay. So if it's continuous, then we have continuous time signal, and if it's discrete, then we have discrete time signal. This is kind of already taught. Okay. But let's say this in more detail once again. Okay. And as we just said today, the continuous time signal. The continuous time signal is the variable is enclosed by a parenthesis like this, and we'll mostly focus on one-dimensional, and so this parameter will be time here. Okay, and then for the discrete signal, okay, this is a bit funny. So discrete signal, the independent variable is also enclosed by a bracket, and although we call it time, we don't use t here. Okay. To better distinguish from continuous time signal a little bit. So usually we use m and n here, but yeah. So that's just a notation, but this is not rigid. Okay. So discrete signal we always use a bracket, and in the middle, usually we use n and n, etc. here, but sometimes you can also put t here. And then the other thing we didn't say, but is very important. The thing we didn't say previously, but it's very important, is the discrete signal. So how it describes is that all the time here are integer value. Okay, so as you see, is 0, 1, 2, 3, 4, 5 here. Okay. Yeah. Yeah. So the spacing here is always 1. Spacing between these kind of sample point is always 1. Each one of them is 1. Okay. And yeah, so that's the convention we take. The discrete signal always have the time value sampled at integer. So 0, 1, 2, 3, 4, 5, and then -1, -2, -3, -4, -5. There is no 1/2, etc. here. Okay. Even yeah. So always integer value. That's just the convention we take here. And good to remember. Okay, any question? That's continuous time and discrete time signal. And so I guess the first important thing to remember is discrete signal. Our convention, we take the discrete time as integer value. Okay, and then let's see some properties of signals. Okay, so as we study signal, a lot of them related to real world life. Real world physical property, and a lot of time we want to study a property that energy and power. Okay. And to give a motivation, we can think about energy and power in a circuit system. Although, in a circuit system that has a signal that's like current and voltage. Okay, So then this equation is just physics. So we can think about what's the power of this system. Okay. So maybe power through the resistor here. Okay. The power through this resistor is voltage times time, the instantaneous power, and you do some physics calculation, and it is voltage squared divided by resistance, or it's current squared times the resistance. Okay, and then we can also calculate the energy consumption over a finite time interval, and the energy will be the power. Will be the instantaneous power integrated over some period of time. Okay, okay. And yeah, so it will just be the P getting integrated through from some T1 to some T2, and and yeah, and then you can put this P in different form. It can be this V squared over R, or this I squared times R, and integrated from T1 to T2 both. And then you can also think about average power. So average power is is P taking average. So basically you need to integrate it, then divide it out by this time interval again. Okay. So it's this integration, then divide by this interval 1 over T2 minus T1. Okay. And so those are energy and power for circuit system. You can calculate it. And what we want to do is we want to take the energy and the power as an abstraction. Okay. So for any one-dimensional signal, we want to define the energy and the power of them, without looking into the detail about the physics. Okay. So here we look into the detail of physics, and we have this R here. So we kind of take an abstraction of energy or power in circuit system, and say if we kind of just ignore this R here because this R depends on system detail, but we see that the power always is always proportional to this signal square, right? Like irrespective of whether your signal is V square or your signal is voltage or current, the power is proportional to the square of your voltage or the square of your current. So it's a square proportional to the square of your signal. So we say maybe we can take an abstraction, and then we just say, okay, we didn't say. I guess that's right here. Okay, so we take an abstraction, and we say, so how about we just define the power is just your signal square. Okay, this is what we think. Okay, so we just define abstract power for whatever one-dimensional signal, and say it's just your signal squared, because in electronic system it looks so. Okay, so that's nice. And although we are losing some physics parameter here, but that's just some constant, so it should be okay. Okay, so we define this abstract power for any signal, and then we can calculate the corresponding abstract total energy, and total energy consumption, and the total average power. Okay. And okay, so the energy is easy. So it's similar. So energy is just power getting integrated. Oh, sorry. So it's square, but okay. So it's going to be useful later. Okay, and so the signal can also be complex value. So actually, we take absolute value sign here instead of just square. Okay. Okay, and yeah, so that's abstract power, and then we have abstract energy. So abstract energy is abstract power integrated over some finite time interval. So from some T1 to some T2, and then we take average power. Then it's this abstract energy divided by this time period. So this x of t absolute value square integrated from T1 to T2, then divided by this interval of 1 divided by this interval of T2 minus T1. Okay, so this is average power. And so those two are the energy and the power for continuous time signal. And we can also have energy and the power for discrete time signal, and it's really similar. So the power is still the same. Okay, so the power is still just this x of t, or more, or no, time is written as n. So power instantaneous power is still x of n squared. And but now this is a discrete signal, so we cannot really do integration. Remember, discrete signal look like this, and so we have still have an instantaneous power, but for energy we just sum over. We just sum over the interval. Okay. And yeah, so if you say we take an interval from n1 to n2, then we sum from n1 to n2. Okay. And yeah, and then if we want to take so it's kind of like, I guess, schematic. It's kind of like we have this discrete time signal here, right? Discrete signal like this. And let's say this is n1 and this is n2, okay? And then we say, and we have those things squared, so so we have power maybe looking like this. Maybe power is like this, and oh, actually, let's say this is already power. So we have a signal, and we already squared it, and so those are powers already. Okay. So yeah, very generally. So maybe this is a P of n here. Okay, P of n. And so what I'm thinking for this discrete is, so the power at this point, so the energy consumption is kind of like from so each dot and corresponding to some unit time. So we just sum together those powers, right? Okay. Yeah. So this is the total energy consumption from this n1 to n2, and it has this correspond to those three rectangles, and also so and also we can take the average power, and that will just be the energy divided by how many time points you have taken, and how many time points you have taken is actually n2 minus n1 plus 1, and this plus 1 is just from elementary school math. So for example here, you can kind of just see really easy from example. So for example, this is 0, 1, 2, 3 here, right? You see this n2 is 3 and n1 is 1. So n2 minus n1 is 2, but you're actually taking average. You're actually taking like 3 time slice. Okay. So you need a plus 1 here. That's just elementary school math. Okay. Any question on energy and power? Okay. If not, yeah. So those are our finite interval, and now we take math a little bit crazier, and we say we can also think about energy and the power over infinite interval, and it's really just taking a limit of just taking the taking your starting and the end of your interval to infinity. So you say it's from t goes to infinity from minus t to t, and we just write this as minus infinity to plus infinity. Okay, so you can have a total energy that integrated from minus infinity to plus infinity, or in case of discrete, and there will be summation from minus infinity to plus infinity. And similarly, you can take the average. So you take this equation, so you take this interval and also push the lower bound and upper bound to infinity. So you divide by this infinite long interval, and you infinite long interval, and you are integrating over this infinite long interval. And similarly for the discrete time case. Okay. And yeah. This is just taking the upper and lower bound to infinite. And so something a bit interesting here is that in the infinite time interval case, then there is something you can derive that is, if your total energy is finite, then your average power will be 0. And this is just really something really trivial. Is because if your total energy is finite, then your power is going to be this finite number divided by your infinitely long interval. So some finite number divided by infinity is going to become 0. And then the other way around, if your average power is not zero, it's some constant, then your total energy is going to be infinite. Because the total energy is going to be your average power times some infinite long time, and it's going to be infinite. Okay. And yeah, we have 5 minutes left, but I think we have finished everything we want to talk about. So, anyone has any question? Otherwise, I think we can stop our class a bit early today. And I will see you on Friday. Okay, yeah. So, that's for today.
Question. Why do you include a negative time interval? How is that possible?
What do you mean negative time? Oh, you mean you mean T1 and T2 can be negative?
Like, why do you consider the negative side of a time interval? Is that possible?
Because you are talking about. Wait, maybe try. You are saying why do we have negative time here?
Yeah.
Because 0 is kind of arbitrary.
So how can you integrate to a negative infinite time interval or any infinite time interval?
Integrate from negative infinite time.
Because time can't be negative, right?
It just usually just means that something has started like a very long ago, a long time ago. Yeah. Yeah. Because 0, I guess the origin is kind of arbitrary, right?
But then you reach a point that's like negative time.
It's just a translation from some time point.
Yeah.
Okay, but like say the time point is 1 or 100.
I guess it's just
like negative.
I guess it's an approximation. Yeah. It's just an approximation for really long ago. So maybe the system just exists really long time ago, and we kind of want to.
Okay.
Yeah, approximate. Yeah.
Thank you.
Yeah.
老师，
刚刚的那个 x
啊，哪一个？
那边是有个 x，
哪一个？我觉得在
在
下面，
就是老师，因为你刚刚有那个 x 的话，我不知道代表是 v 还是指的是在下就是在英国的时候，这代表是 v 还是 r？因为我现在就有点搞不懂，因为你突然跳来跳去，我就
没有，这个是 any signal， 这个 x 是 arbitrary signal。
那跟老师刚刚讲的
这个只是
不一样。
就是 K 是 V 也可以是，不会是 R 不是 signal，V 或 I， 它可以是 V 也可以是 I。我是说，就是这个看起来，就是不管你是 V 还是 I， 看起来都是正比于它的平方嘛。那我们就说任意的 signal 我都定义一个 power 是它的平方这样子。
那老师，我想请问你有没有做过2维的图像的，就是在讲 FFT， 然后如果有做过2维的图像的讯号这样的，因为我想要请问一下，因为我在论文上看到的话
2维图像讯号，2维我们会讲比较少，但是你想讲什么？
因为我在想说为什么
之类的吗？
对，因为我不知道为什么在那个就在论文上啊，就是大概找了一圈，然后 FFT 会比较少，不知道为什么会是只能说一个 FFT 就是 Fourier Transform。Face
Fourier Transform 吗？那2维应该也可以做吧？这样，什么意思？不是你要用来做什么？你可以做啊。
例如说把那个杂讯给去掉，那它是不是 FFT 的话，就是用在 image 的讯号上面比较不好用？因为我看太少人在做这块了，然后
杂讯其实我们好像有类似的 slide， 看你。对啊，你还是一样可以做 filter 啊，所以好像也没有不行吧？是这一张吗？我找一下，是被我砍掉了。不然你说不定可以翻一下课本是。我想想看是丢在哪里。第2章吗？的确是有2维的 filter 嘛，就是你一样可以 FFT， 你也一样可以做 Fourier Transform， 然后去 filter out 的一些高频的东西之类的。对，
可是它的效果是不是比它好？
效果就不知道了。对啊，像我们这里有 example 之类的嘛。下一章，对啊，有2维的。对啊，看你想要做什么事情吧。效果的话就是实际考这样的嘛。
因为我只是看好像没有。
像我们这里有什么 edge decoder， 有什么 edge detection 或者什么 smoother 之类的，这都可以做2维的。对。
所以如果是那种 种比较简单的图片，它的效果会比较好。像是因为
那我就不知道这个是比较实际的东西，你要看你实际的效果怎样的。我们是很 general 的 class。
我像第三个是，我想请因为我是想要旁听，然后想请老师帮我加到音段，可以吗？
哦，可以啊，如果是要旁听的话。好。那你先等好，我先看，我看这可不可以？我需要打密码，不需要。OK， 那我现在直接加好了。课程，我先把这拔掉好了，不用给大家都看。那我算了，我好像不太能多攻，所以我先加你。你知道旁听，所以你是大几的学生啊？为什么是旁听？哦，你是硕二。
对，因为我是想要补需要语系统。
硕二那不是应该修过好？不管，那我加。那你1006，有什么鬼？为什么他在说106 25 92？好像没有旁听是我搞错吗？应该没有打错。
那
为什么？
还是要申请什么东西？我这里要申请。
应该不用啊。
06 2592。要写加入是那个吗？
但是它通常应该这里要出现你啊，还是我送你的其他关键字名字吗？
可是我的名字的话，是因为中间字有一个特别字，我不知道老师这里。
还是 email 我也不知道。他说学号名做 email， 还是说062592，这样子可以收到吗？没有好吧。那我们先问其他问题好了。
没有那个老师这门课考试都会在礼拜5吗？
对，要礼拜5。
然后我确认一下，所以每个礼拜都会有作业。
对，每个礼拜都有作业。
好，那作业是课本习题吗？还是？
对啊，基本上课本习题。
然后
大部分
习题，然后习题会再 announce。就是哪几题会再公布的？
对，我们基本上会把题目打出来啊，对。一打出来的位置。
在议论上。
对。
好，OK。
我是直接寄 email 给你，然后你直接加。
我觉得你现在试试看好了，你自己试试看。大家怎么才找到你？加圈可能有点快。你们是什么系的？资工。电机系可能，可是电机系你们开很多课，电机系。
现在他们都选吧。
对啊，但我可能没有办法，我是以资工系为主，而且我们资工系都签不完了，因为我不小心那个。
电子班的。
对吧？可能还是有点困难，主要是我们教室不够大，所以对吧？我这个不小心签了太多外系的人，对。对啊，真没办法。你们还是可以送表单啊，反正礼拜5前如果有办法，我试试看。对啊。
然后如果有空的特选的话，可以就是在。
对啊。礼拜5选。基本上啊，但是也是看有没有人退吧。反正我有一个上限是100人啊，对啊，就是这样。对啊，就是这间教室的上限。
然后不好意思因为我是一个重考生，然后我现在大一的课都抵掉了，然后每次我去一个教室的时候，然后教授都会觉得说我是大一的，然后怎么都不修微积分那些的，然后变成说我现在都没有那个课可以选，如果没有课的话，可能会必修。我不知道可不可以就是可以再帮我。
可是这里不能社交吗？
教室大小，请问就是教室大小就是如果
教室大小麻烦是考试的时候，因为如果超过教室大小的话，考试太多人很麻烦。
然后可以再就是拜托一下，就是如果有。
所以你是哪位？如果
有空缺的话。
但是如果只是要修课的话，应该有很多课可以修吧？
对，但是就是因为下午是实验课，然后就被占，就刚好就真的就只有这堂课必修课可以那个。对。
那我可能再考虑一下，你再寄个 email 给我吧。
好，谢老师。
等一下那个你是叫什么名字？
我有交表单。
你有交表单？
我插电，然后我叫胡家伟。
因为开头要加填 email 我都没有回。 你有记过吗？还是？
然后我没有记过，然后因为我一开始就是想说这两科是大3、大2、大3就是
对，但是不知道为什么有这么多人要签到爆满。
然后我就发现没有老师愿意收的，所以我就觉得应该可以挑战看看这堂课。不好意思。
但是好像是，不过你说你大一又修过的。
对。
要怎么讲？
你要说什么？
要怎么讲？
不要乱翻。请不要乱翻这个。
不好意思，那
对啊，
个因为我在想说，
所以你是怎样？你是硕士生，通常可以加。我觉得你的系统是不是很奇怪？我不知道。通常硕士生是可以收到。
我要先申请还是？
没有啊，通常是我这里可以找得到啊。所以我不知道你的是怎么回事，为什么没有你的学号的？还是你搜你的名字？
可是我需要
然后同学你就先寄个 email 吧，但是很困难。
老师可以加个仓颉吗？我加一下仓颉。
不要。
不要吗？那。
对，你先打，不然你 email 好了，你打 email。
打 email 吗？
对。
可是我刚打 email。
还是因为你的名字？这里看起来有 ，OK， 那刚刚为什么没有？11有啊，好不管，总之成功了。然后你现在是旁听生了。
老师这个这样可以。
对，这样就有了。
可以，那我可以再检查一次吗？不然的话我就觉得检查一下，吗？可以吗？
不用啊。
不用吗？
应该有吧？不知道。
那个可以搜寻吗？106。为什么？
不知道好，不管，总之就是这样。我可以换个旁听生。好，你来这里，好，恭喜。